Hi YouTube, so in this tutorial we're going to be going over how to implement a queue in C. So first, let's just go over the theory of what a queue is. So in programming, it's the exact same as real life. A queue's got a front and a back. And people start lining up to the queue from the back. So as people come, they line up one at a time. First person in there is at the front of the line. And as people leave the queue, they leave from the front, and so on. So what we like to say is that a queue is a first in, first out system. And we've only got a sequence of items, one after the other. So all we really need is a linear sort of data structure. So let's start thinking about how we might implement this. So as we only need one element after the other, we don't need any complex graphs or anything. We can use maybe an array or perhaps a linked list. Let's have a look at how we might do this with an array. So we'll start with an array and initialize some number of elements. So let's say we start off with 1, 2, 3, 4, 5, 6 elements. Now, we need to keep track of where the front and the end of the queue is, of course, so we know where to add and remove people. And we're going to switch this around because arrays easiest to work from index 0. So we're going to add people from index 0, so on, and therefore 0 is going to be the front of the queue. So it's going to be the other way as the previous example. So we've got front of the queue is generally going to be towards this way, and the back is going to be towards that way. So as we add people to the queue, let's say this is a queue for your morning coffee, and Jack gets here first, is waiting to be served, then Tom rocks up, and then Steve. Now as people are added, when Tom rocks up, the back of the queue moves to Tom, of course, and when Steve rocks up, back of the queue moves to Steve. Now, when the barista, say, starts serving people, what we do is Jack's going to be served first. He's going to go and enjoy his morning coffee. And the front of the queue then moves to Tom. Say Tom gets served, Tom goes and joins Jack with his morning coffee, and the front of the queue moves to Steve, who is also the back of the queue. But now let's say we add 4 more people. So Mike rocks up, followed by Liam, followed by Rodney. And the back of the queue is now at Rodney. And then let's say Norton also wants a coffee. So Norton rocks up, and the back of the queue is currently at an index of 0, 1, 2, 3, 4, 5. So the back of the queue is at index 5. This means that the next element we should add should be at index 5 plus 1. That's how we've been doing it previously. But that would be out here at index 6. Now, we lose track of Norton because that's outside of our defined array. So what we can do is, instead of adding Norton in at index 6, we add 1 to the back of the queue and then mod it by 6. So 5 plus 1 modulo 6 equals 0. So what we instead do is we add Norton at index 0, and as people keep lining up and getting served, the array goes around and around, and suddenly our problem of keeping it going is solved. So now the back of the queue moves around to here, and we've effectively turned our linear array into a circle. But now what happens when we say have more than 6 people? Well, what we can do is we can start with a larger array, but that's going to keep more memory. So what if we don't know how many people we're going to have? So we can start with an array of size 6, and every time we want to add a 7th person, we can use the C function, realloc, and find another chunk of memory where we can fit 7 elements, and it'll copy the current contents of the array over, and then we can keep going. But then every time we want more than the current amount of elements, we're going to have to realloc again. And if it can't find a consecutive additional number of spots on the end of the current array, we're going to have to the system is going to manually copy every existing element of the array across. So this is unideal in terms of time complexity. Also, using realloc can get a bit confusing. So it's perhaps easier to look at a linked list method of implementing a queue. So let's see how we could do that. So with a linked list, we don't really have to worry about running out of initialized memory. And this is because when we initialize a linked list, each element sits in its own chunk of memory. So say we've got a pointer down here and some data up there. When we initialize the second element of a linked list, we'll find another piece of memory. It doesn't have to be next to it, most likely isn't next to it. And the pointer of the old linked list will point to this new one. Now, even if we have a bunch of other memory being used by our program, as long as there is enough consecutive memory to store one element, we can always add a new element onto our queue. So this both gets around the problem of having to shift every array element over every time we run out of space, but also means we don't need the queue to be stored in consecutive memory like an array. So in this sense, it would be beneficial to use a linked list system.
Alright, now to let's implement the code,
talk about how we might actually implement this as a linked list.
Start by setting out a file. So we're going to have a C file and an H file for our queues,
so with
because we're going to be doing this as an abstract data type.
We keep track.
That way,
in a basic linked list, we keep track of
program in main.c. We can't
the data for each node
edit the underlying structure
and a pointer to the next
individual elements. We can only do what we define we can.
And so our overall queue as itself is simply going to be contained in
header files we need. So standard
perhaps
input,
the
output,
first element.
We need the standard library.
So this is going to be our node structure.
Because malloc and free, etc.
And this is going to be our queue structure.
And if we're using linked list, of course we need that. We also
we may notice that whilst we need to keep track of first, so we know who to pop off the queue
been allocated properly,
in which order,
and of
we also might want to keep track of the last element of the queue.
We also need to include, our
because we need to know where to add people.
Alright, so now let's jump over to our header file and have a think about
our linked list structure is going to have a head, which is the first element.
What functions we want to write for our queue. So, for starters, we're going to need to do a type def.
And a tail,
so that,
which is the last element.
Oh, sorry.
And as we add elements to the queue, we put them on the end of the tail.
Which we haven't done yet, so let's do that. So, first of all, we're going to define a struct for our queue.
And as we pop elements off the front,
so let's define a struct
we pop them off from
Make sure we keep our semicolon in there at the end.
So let's get into writing it.
And our queue is going to have, let's say we're storing integers, so some int data, and we're going to have a pointer to the start of the queue, because that's where we're going to pop stuff off from. So before we do that, we need to define our nodes. So we're going to use another struct to define each individual node element of the queue. So that way, when we have a pointer to the first element, it's going to be a pointer to a node. So struct node star, let's call it the front. And we're also going to have a pointer to the back of the queue, because we need to keep track of that every time we add something to the queue. Okay, so then what are we going to store in our node? Well, obviously, we're going to store the data in the node, not the queue. Apologies, that's on me. And we're also going to store a pointer to the next element. Alright, so now we have the definitions. Let's finish that type def. So we're going to type define a struct queue star as, so a pointer to our queue structure as just queue with a capital. Alright, now let's think about what functions we want. Now, of course, the most obvious one is initializing a queue. So we're going to be returning a pointer to a struct queue, so we're going to be returning a queue. Let's call that new queue. Doesn't need any inputs. We of course need the opposite of this, which is going to be destroy queue, because when we're done with it, we need to destroy it so that way we don't have memory leaks. We also need to add elements to a queue, so let's call it queue add. Add elements to a queue, we need to be able to pop things from the queue or take stuff off the front. So we can call, it's called different things. You can call it DQ. I'm going to call it pop. So let's call it queue pop. So pop is a programming term used in different things: queues, stacks, even arrays. And a pop is a function that does two things. It edits the underlying data type itself, removing the specified piece of data, and then also returns that data. So it's important to understand that a pop is like a function that both edits another piece of data, like it both edits an underlying piece of data and returns extra data. So we want to be able to pop things. What else do we need to be able to do? That just about covers it. We also might want to add some other useful functions, such as returning the size of the queue, just so we can see how many elements are in it. And say similar to pop, except this maybe just peaking at the front element. I'll change that to queue size, be consistent. Let's peak the front element. So queue peak, and takes a queue as an argument. Alright, so let's go with those functions. So first of all, new queue. Alright, so to initialize a new queue, what we're first going to need to do is allocate the memory required of an instance of a Q struct. So we're going to malloc the size of a struct Q. Sorry, there we go. Now what we're also going to need to do quickly is just check that that memory was allocated okay, we hadn't run out. So first of all, if new equals null, it's a null pointer, no memory was allocated. Let's print no memory to allocate Q. Just for debugging purposes, and let's exit the program because there's no way we continue if that fails. So, okay, so now we've allocated the memory to our new Q instance. We now need to initialize its values. So first of all, we've got a front and a back, and let's, as the queue is currently empty, they can both be null. It's important that even though we're initializing them to null, it's important that we actually initialize them because we don't want to be dealing with uninitialized pointers. That'll give you an error very quickly. Last thing we need to do is return the new queue. Alright. Now let's do the opposite. Let's destroy the queue. So what we need to do is loop through each element of the queue, freeing each node until the queue is empty, and then at the very end we need to free the struct queue itself. So an easy way to do this is to use a function that we haven't written yet. So while the queue front isn't null, what we're going to do is we're going to just keep popping elements off it, which will destroy them for us until the queue's empty, and then what we're going to call this free. Okay, so we're going to leave that to be continued. So free, there we go, free the memory at Q. Alright, let's quickly write that add function. So adding an element to the queue, what we need to do is first we need to make a new struct node element. Now we can do this we first need to use malloc to allocate the memory. So make a pointer to the node, struct node star, let's call it new node. And we need to allocate the size of a struct node. And then we need to initialize the values at the node. Now I forgot to do here, whenever we add an element, we actually need to add a piece of data. So what we're actually adding. And that way we can initialize that the new node's data is the data we're given. And also we know as we add nodes, we add them to the back, so we can right away initialize the new node's next to be null. Alright. Now what we need to do is we need to actually put it in the linked list of the queue. So all that requires is accessing the back of the queue like this, and then simply saying, because the back of the queue is a node, we can also access the next element of the node, which at the moment should be null. It's at the back of the queue, and we can set that equal to our new node. Then the last step is to simply reset the back of the queue to be what it is now. So the element that we just set to point to new node is now the second last element of the queue, and we changed that pointer, that back of the queue pointer, to be now pointing at the node we just created. And now it's complete. Alright, next up, queue pop. Now this is the function that we're going to call back here. So, queue pop, we need to make sure we're freeing all the memory we allocated with each node after we're done. So that way we don't have memory leaks in our program. So remember, we're popping from the front because this is a first in, first out system. So first of all, what we need to do is we need to cache. What I'm gonna do is, because we're freeing the node, but we also need to return the data, we need to store the data somewhere. So let's call it output before we free the node, because otherwise we're just going to lose the data we're supposed to return. So it's going to be the data in the node that's at the front, in the node that's at the front of the queue. That's just output's one word. Alright. So now that's stored, we don't need the queue front, that first element anymore. We can get rid of it. So we can simply free queue front. Boom. Now, finally, what we do need to do is we need to move where queue front is pointing to queue front next. However, we've lost that because we've already freed queue front. So what we actually need to do is we need to also cache the next value. So struct node star the next front, we'll call it next. Can be queue front next. Boom. So now queue front is going to just become the next element. Easy. And last step is we simply need to return output, because that was the data associated with that first element. Alright, so queue pop is now written, which means we can finish our destroy queue, and all we need to do is call queue pop on the queue that we were given. Easy. And because that edits the queue as we go, we don't actually need to do anything with what it returns, because we don't care what's being popped up every time. And that way the queue is going to change, and eventually the front should become null, because when we pop the last element, the front becomes the next element, and we're done. All right. Q size. Now, what we could do with Q size is have a counter and iterate through until we reach the end of the queue. And that way we calculate the size each time. Except, unfortunately, that means we have to loop through the queue every single time, and the queue could be really large. So what I instead would prefer to do is actually keep track of the size of the queue in the struct itself. And that means we need to go back and edit our code a bit. So now we're keeping track of the size. Whenever we create a new queue, we need to initialize the size to be 0. Destroy will not change. Queue add. We need to increase the size, of course. We've got one more element in there. I'll write it out, looks neater. And whenever we pop an element off, we need to decrease the size. All right. So now to return the queue size, it's a lot more simple than it was before. We simply return queue size. It seems stupid, but remember, because we're using an abstract data type, we can't actually access the queue size outside of this program. For example, in our main program. Alright, now that size should be working, we want queue peak. So queue peak is kind of like queue pop, except we're not going to be freeing any memory or actually deleting the nodes. The queue remains unchanged. So in that sense, it is a very simple return of the queue front's data. So the data of the first element of the queue. Alright, so that's our linked list completed, but we haven't really thought about boundary cases. For example, what happens if we call these functions on an empty queue? So obviously we can't call new queue on an empty queue because it's a void function. It takes no inputs. But what happens if we try to destroy an empty queue? Well, on an empty queue, the front should be null, so it won't enter this loop. Then it will simply free the queue. It'll be fine. All right, queue add on an empty queue. Queue front will be null, so we'll queue back, but we don't seem to use them. That'll be fine. Alright, but what happens when we call queue pop on an empty queue? Now this is going to give us an error because queue front is a null pointer, so we can't access data or next in it. So what we do need to do is we need to check if queue is empty. So first of all, one way to check it is obviously to use the new value we just created. So if queue size is 0, queue is empty, then we have a choice to make. We can either kill the program and throw an error just to show that there is an error in the program, or we can return something else to make it clear that there was an error. So if you're using all integers could be in the program, it doesn't really make sense to return a value, because that way you could accidentally return the value legitimately, like that value was in your queue when you returned it, you popped it off. But say you were only using positive integers in your queue, you can do something like what I'm about to do. You can define a constant, call it empty error, and make it a negative number. I'm going to call it -1. Or you could, if -1's going to be in your program, choose another integer. But make sure it's one that won't ever be in the queue. We're just going to return empty error. And that way, I spelled empty wrong. I spelled it wrong again. And that way, program won't kill, so we can keep running. And we know that we tried to pop off an empty queue. Alright, so returning the size of an empty queue, size should just be 0, that's fine. And peak is going to throw the same issue. So we simply do if the queue size is 0, return empty error. Alright, so that should work to test this. Alright, so even though we haven't written main.c yet, what we can do is try compiling our program, hash include, just to check that there's no syntax errors. Alright, implicitly declaring a library function printf. Standard input. That's right, I forgot to include standard input output library. And let's also include... Alright, so now that we have included the standard IO library, what we can do is we can try compiling again. And of course, we get this error function because we can't compile a C program without a main function, because every executable needs a point to start. So what we can do is go and write a very skeleton main function. Alright, so now we have a skeleton main function. Alright, what we can do is try compiling again, this time with main.c, and no errors. So now in our main function, I've written this very basic main function to test the functionality of our queue. So what it does, firstly, it initializes a new queue, of course. It then reads in one integer using our new queue, and while it successfully reads in that integer, so if it reaches the end of file, it won't read in anything. And how do we want to do this? So let's test it calling integer an argument. So if you enter a 0, entering lines what it does is it grabs the next integer, so you can enter a 0 followed by like 0 space something else, and it will add that integer to the queue. If it encounters a 1, then it will pop off an item of the queue and print it. If it encounters a 2, it'll peek the next item of the queue and print it. And if it encounters a 3, it will print the size of the queue. Formula is... Let's see if it works. So I've compiled the program with the new version of main.c. So let's run it. Length, let's define that here. Okay, so let's start by trying to see what the size of the queue is. 0, perfect. Try popping off an element from empty queue, it gives us -1. Remember that was our empty error value. And similarly, if we try and peek, let's say the max line length we can enter is 100 characters. Let's try adding something. Let's add an 8. Alright, as we can see, we got a segmentation fault. So now, while that means that we need to review our program and find an error in the queue add function. Alright, so what we notice in the queue add function is that when we're adding to an empty queue, we're trying to access the queue back, even though it hasn't been set yet. And we don't even do anything with queue front if it's an empty queue. So obviously I skipped over that when we were considering what happens to an empty queue. So if the queue size, is 0, what we can do, what we need to do is we need to set the, let's put that under there because we still need to make the node. So if the queue is empty, to accept, what we need to do is we need to simply set both the back and the front to be this new node. because it's the only element
An
in
integer.
the queue. So and we don't want to do anything else if that
And
happens.
let's say that
So we'll wrap this in an else statement. So remember, scanf returns how many items it read.
Alright,
so
let's try it
read
out.
an integer. Alright, so now let's try updating. Let's try compiling our updated program into current. So main.c q.c. Cool, compiles our errors and try running it. Perfect. So while popping off an empty queue, it's still 1, size is still 0,
Let's say
peak
greater
is
than
still
0, but it's
empty
only
error.
ever going to be 1 or 0.
Let's try adding an 8 to
So
the
while
queue.
red is greater than 0, that means it read at least one
Let's
character.
try peaking, should give us an 8.
What we're going to do
Cool.
is we're going
Alright.
to do
So we get an 8 when we
Queue.
peak. If we try and peak again, because it didn't change the queue, it should give us an 8 again, and it does. If we try popping
add
off, should give us an 8.
into our new queue.
And now if we try peaking, it should give us an empty error. Alright, let's try adding a few more elements. So we add an 8,
the number that we just read.
7, maybe a 3, and a 10.
Let's say
Now,
every
the first
time we
item
read
to be
in
popped off should be an 8. Great. The next one should be 7, 3, and 10. So it comes off in the order it went on, first in, first out. And our queue's working.